couple of lectures and tutorials, we've been looking at truth tables and the truth tables for compound propositions, complex formula made up of a number of simpler sub-expressions. And I pointed out on occasion that it's actually the result of those truth tables are sometimes the same as the result of other simpler formula. And this gives us a motivation for our first proof technique called transformational proofs. And in the transformational proof, we're going to change or transform a formula into another, what we call logically equivalent formula. And it means that anywhere we could have used the first formula, we can now use the second formula instead. Now, one of the motivations for doing this is that we've already seen that the size of the truth table grows exponentially. So if we have one prime proposition involved in a formula, there's only 2 rows in the truth table. If there's 2 prime propositions, then there'll be 4 rows. 3 prime propositions, it'll be 8 rows. 4 prime propositions, 16, 5, 32, and so on. So it's 2 to the power of n, where n is the number of prime propositions involved in our formula. And if we have a complex formula that has got 10 prime propositions involved, then we've over 1,000 possibilities. And if we've got and the last day we saw where we can have a correspondence between the proposition logic we were talking about and the Boolean logic that's used in hardware. If we've got a complex chip that has a million or a few million transistors involved, then it means that that technique of using truth tables is no longer sustainable. So, to start off, we define, we make 2 definitions. One, logical equivalence, and the other, logical implication. We say that 2 formulae are said to be logically equivalent if and only if their equivalence is a tautology. Remember, we had tautologies the last day, and essentially a tautology says that 2 formulas have exactly the same truth value for all possible combinations. So the 2 formulae then will have exactly the same truth table, so in other words, they're identical in meaning. And as I suggested a minute ago, that means given an occurrence of one, we can replace it with the other without changing the meaning. And that goes for sub-expressions as well. So if we have in our large formula, we've got a sub-expression, and that sub-expression is logically equivalent to some other formula, then we can replace the first expression with the second one, and the overall meaning of the formula will be unchanged. And then the other one, which we're going to make less use of, but nevertheless we will make some use of it, is the logical implication. And we say that a formula P is said to logically imply a formula Q if and only if their implication is a tautology. So if P implies Q, if that implication is a tautology, then we say that the one formula logically implies the other formula. And in order to build up, I suppose, a set of techniques that we can use in our transformational proofs, we collect together a set of what we call logical laws. And these all come from Nisanka's book and will be made available, as will this lecture. It'll be made available later today. So I'll also put up a sheet with the logical laws that are taken from Nisanka's book. The first of these is the commutative laws. And the commutative laws say, there's 2 of them. The first says that P and Q is logically equivalent to Q and P. The second one says that P or Q is logically equivalent to Q or P. So this symbol in the middle here with the equals with an extra line in it And we'll sometimes have this with arrows on either side as well. So we'll use that symbol with arrows on either side as well to stand for logical equivalence. So what this says is that if we have a formula P and Q, we can replace it with Q and P, and the meaning of the overall formula is unchanged. And similarly, if we have P or Q appearing in a formula, we can replace that with Q or P, and the formula will be unchanged. And you can think of many of these logical laws have analogues in arithmetic or mathematics. So P multiplied by Q, or A multiplied by B, is the same as equivalent to B multiplied by A. And A plus B is equivalent to B plus A. So some of these laws will have analogues in arithmetic. So those are the two commutative laws. Then we have two associative laws. And the associative laws, the first one says that P and Q and R is logically equivalent to P and Q and R. So if we have got an expression that involves two conjunctions, then effectively it doesn't matter which order we do those conjunctions or which we apply those conjunctions. So if we have a formula which says do Q and R first and then do P and the conjunction of Q and R, that's the same as if we did P and Q first and then we did the conjunction of that with R. And again, the arithmetic analog of that would be A multiplied by B multiplied by C in brackets is equivalent to A multiplied by B multiplied by C. And then there's a similar associative law for disjunction. So P or Q or R is logically equivalent to P or Q or R. So again, it doesn't matter in which order we do these. So if we have Q or R to be done first, and then we have the disjunction of that with P, then that's the same as doing the disjunction P or Q first, and then doing the disjunction of that with R. And in fact, because of these associative laws, we sometimes drop the brackets. Even though strictly speaking, the conjunction only applies to a single proposition, compound proposition on either, a single proposition on either side, we often drop the brackets here. So P, we just say P and Q and R. In the same way that even though multiplication is a binary operation, and strictly speaking we're supposed to say A multiplied by B multiplied by C in brackets, we'll often just have A multiplied by B multiplied by C. And the same for plus and disjunction. The distributive laws, again there's an analog to at least to one of these in arithmetic. So P or Q and R is logically equivalent to P or Q and P or R. So we say that disjunction distributes over conjunction. So if we have this formula, Q and R, and we have the disjunction of that with P, then that's logically equivalent to having the disjunction of P and Q, the disjunction of P and R, or P or R, and then having the conjunction of the two of those. Okay? And then the other distributive law is where conjunction distributes over disjunction. So if we have Q or R, and then we have P and Q or R, then that's logically equivalent to P and Q or P and R. And in fact, this is the one that has the analog in arithmetic. So if again we replace the conjunction with multiplication and the disjunction with addition, then if we have A multiplied by B plus C, that's equivalent to A multiplied by B plus A multiplied by C. Now it doesn't work the other way. So this one doesn't have an analog in arithmetic. That analog breaks down there. But the analog does work for the second of these distributive laws. Now you can argue, or you might point out, well, this isn't actually simplifying things. Okay, so here we have three propositions and we have two operations, and on the right hand side we have four propositions and we have 3 operations. So that's not actually simplifying things at all. One of the points of these logical laws, and an important point, is that they apply from right to left just as well as they apply from left to right. So we can replace this left-hand side with the right-hand side, but we can also, if we have something of the form of this right-hand side, we can replace it with the left-hand side. So these logical laws apply from right to left just as they do from left to right. And that applies for the previous ones that we've seen as well. 2 of the laws that we're going to be making most use of, and you'll come across this in your computer architecture course as well, are De Morgan's laws. And we've already had an insight into at least one of De Morgan's laws already. De Morgan's first law says that the negation of P and Q, the negation of the conjunction P and Q, is logically equivalent to not P or not Q. And let's just examine the 2 of these. So with P and Q, we have P and Q, we have not P and Q, and then we also have not P, not Q, and not P or not Q. So we have our 4 possibilities. We write them down in the correct order: true, 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 false, false, true, false, false. P and Q will be true only when P and Q are both true, and then not P and Q will be false when P and Q are true, and it'll be true when P and Q are false. Then we have not P, which is the logical inverse of this column, so it's false, false, true, true. And then we have not Q, which is the logical inverse of that column, so it's false, true, false, true. And then we have not P or not Q. False or false is false. False or true is true. True or false is true. True or true is true. Okay. Now, there's 2 ways to determine whether these 2 formulae are tautology. So one is, are the same. So one is just simply to point out that the 2 columns are the same. The other is to actually get the equivalence of these 2 columns. So we have not P and Q is equivalent to not P or not Q. So false equivalent to false is true, true equivalent to true is true, true equivalent to true is true, true equivalent to true is true. So here we have a tautology. So the 2 ways of determining whether 2 formulae are logically equivalent is, first of all, to actually look at the truth tables and determine that, or the second is to actually get the equivalence. And if the equivalence is a tautology, then the 2 formulae are logically equivalent. Okay. So you can see that not P and Q is logically equivalent to not P or not Q. So take a couple of minutes now and do the second one in exactly the same way. Okay. So show that not P or Q, the negation of the disjunction of P and Q is logically equivalent to not P and not Q. And these are two formulae that we're actually going to make big use of throughout our proofs, and not just in our transformational proofs, but also in our deductive proofs that we'll be doing after, and then also when we use the predicate logic. And this is just one we had before, where we had not P or Q, not P or not Q, and not P and Q. To think of this, how to apply, and again, De Morgan's laws apply from right to left, just as they apply from left to right. So, and the technique is, and the way I like to present it is that if we have a negation outside the brackets, and all of the operators inside the brackets are the same, then it's an occasion to apply one of De Morgan's laws. So if we have a negation outside brackets, and inside we've got all conjunctions, then it's an opportunity to apply De Morgan's first law. If we've a negation outside brackets, and inside the brackets we've got expressions combined using disjunction, then it's an opportunity to apply De Morgan's second law. And the way to think of it mechanistically is we can bring the negation inside the brackets, we apply it to each of the expressions in turn, and if the operator combining those expressions is a conjunction, it changes to a disjunction, and if it's a disjunction, it changes to a conjunction. Okay, so that's a sort of a mechanistic way of thinking of it. You can bring the negation inside the brackets, it applies to each of the sub-expressions in turn, and if we have conjunctions, they change to disjunctions. If we have disjunctions, they change to conjunctions. Okay? So those are De Morgan's two laws. The next law we have is called the law of negation, sometimes also called the involution law, and that says that the negation of P is logically equivalent to P. So if we have a formula P and we get its negation, and then we get its negation again, then we end up with the original formula P. So the two negations, in a sense, cancel each other out. And the analog in that in arithmetic would be that if we have a number x, then minus x is the same as x. We have two laws together which form the complement laws. The first is called the law of excluded middle, and that says that P or not P is logically equivalent to true. And this comes from the fact that we've got a binary logic. We've only got a two-valued logic. So if we have a formula P and we have another one not P, and they're combined using disjunction, then that overall formula is logically equivalent to true. And because either P is true or it's not true, there's no other, it's either true or false, there's no other possibility. And similarly then, the law of contradiction says that P and not P is logically equivalent to false. And that says that P can't be true and not true, or can't be true and false at the same time. So P either has to be true or not true, true or false. That's what effectively the law of excluded middle says. There's no other possibility. The law of contradiction says that P and the negation of P is always false. And those two laws together form the complement laws. Then we have what's called the law of implication. And the law of implication says that P implies Q is logically equivalent to not P or Q. And this is an important one. So let's just go through that one as well. We've already met it actually in one of our examples, but just to go through it again. So again, we've got our four combinations, P and Q. And we have got on the left-hand side, P implies Q. So that's true, false, true, true. On the right-hand side, we've got not P. So it's false, false, true, true. And then we've got not P or Q. So not P or Q is false or true is true. False or false is false. True or true is true. And true or false is true. So again, these two columns are the same, and if we were to do out the implication of P implies Q implies not P or Q, so true, equivalent to true is true, false equivalent to false, true, true, true. So again, we've got a tautology here. Okay, so this is an important law. It allows us to replace an implication with two other, in a sense, simpler operations, namely a negation and a disjunction. Another law that we're going to use, maybe not as often, is called the contrapositive law. The contrapositive law says that P implies Q is logically equivalent to not P implies not Q. So in other words, we know already that P implies Q is not the same as Q implies P, but this does establish a relationship where we swap around the two operands involved in implication. So we can actually change the two operands as long as we can negate both sides. And then the law of equivalence, last on this slide, says that P equivalent to Q is logically equivalent to P implies Q and Q implies P. So in a sense, we can think of this equivalence operator as being a combination of these two arrows. P implies Q and Q implies P. Now, in many presentations of formal logic, you only have three basic operators. We've presented five: negation, conjunction, disjunction, implication, and equivalence. But in many presentations of logic, you only have three operators, namely negation, conjunction, and disjunction. And these two laws in this page, the first one and the last one, show that you actually only need the three. That the law of implication, the law of implication says that implication is equivalent to a negation and a disjunction. So if we have got negation and disjunction, then not P or Q is logically equivalent to P implies Q. Similarly, equivalence can be made up using two implications and a conjunction. So if we have P implies Q and Q implies P, then that's logically equivalent to, that's the same meaning as P is equivalent to Q. And that's why in some treatments of formal logic, you only have three operators: negation, conjunction, and disjunction, because you can build up implication using negation and disjunction, and you can build up equivalence using implication and conjunction. There's two logical laws of idempotence. One says that P or P is logically equivalent to P. The other says that P and P is logically equivalent to P. So in other words, if we have two expressions that have got the same propositions involved, the same meaning, then we can drop one of them and there's no change to the overall meaning of the formula. Similarly, if we have two sub-expressions that are the same combined using conjunction, we can drop one of them. And this can allow us to simplify overall formula. So P or P is logically equivalent to P. P and P is logically equivalent to P. Then there's a number of laws of simplification. And some of these have got analogues in arithmetic as well. So P and true is logically equivalent to P. P or true is logically equivalent to true. P and false is logically equivalent to false. P or false is logically equivalent to P. The analogues in arithmetic would be that if A multiplied by, or X multiplied by 1 is equivalent to X, whereas X multiplied by 0 is always 0. And X plus 0 is always x. Okay, so there's equivalences to, or analogues for some of these in arithmetic. These are important because it means that if we have a formula that it has, where part of the formula evaluates to true and it's combined with another expression using conjunction, then we only have to look at that other expression, because the part that's equivalent to true is just P and true is logically equivalent to P. Similarly, if we have got a sub-expression and a couple of sub-expressions combined using disjunction, and one of the sub-expressions evaluates to true, then the whole formula will evaluate to true, and so we don't have to care about the other part. The whole formula will evaluate to true. If we have two sub-expressions combined using conjunction, using and one of them evaluates to false, then the whole formula will be false. So false and anything, doesn't matter what anything is, will be false. True or anything will be true. True or anything, sorry, will be true. True and something will be just the something. And finally, if we have two sub-expressions combined using disjunction, and one of them is false, then we can forget about that part and just concentrate on the other sub-expression. So P or false is logically equivalent to P. And this is at the basis of much of the simplification that we can do in formula in our hardware design and also in our software design. And in fact, for those programming languages that allow for what Python would call, for example, the short-circuiting of evaluation of logical expressions. So in Python, not all of the expressions will be evaluated in a logical expression if the Python interpreter can work out in advance what the result of the expression is going to be. And one of the ways it will do this is that if it's got a number of formula combined using conjunction, and one of the formula evaluates to true, then the whole formula will be true. And using disjunction, and one of the formula evaluates to true, then the whole formula, the whole expression will be true. And similarly, if there's a formula which has a number of sub-expressions combined using conjunction, and one of the formula evaluates to false, then the whole formula will be false. So it is an important simplification technique. So that's the first set of laws of simplification. The second set of laws of simplification maybe are a bit less intuitive. They say that P or P and Q is logically equivalent to P. So if we have P and the disjunction of P and something else, then it doesn't matter what the something else is, the result of the overall formula is just going to be P. And similarly, if we have P involved in a conjunction with P or Q, again, it doesn't matter what Q is, the result of the overall result of the formula, or the result of the overall formula, is going to be just P. So this, again, allows us to simplify a complex formula into a simpler one. And I should also mention that, again, all of these, even though we're going to use them mostly from left to right, and we're going to use the laws of idempotence from left to right, and we're going to use the law of implication, contrapositive law, and law of equivalence from left to right, they also apply from right to left. So we can replace this formula with P equivalent to Q, we can replace this formula with P implies Q, and we can replace not P or Q with P implies Q. Then there's two other rules that are sort of like meta laws. The rule of substitution says that we can always substitute a logically equivalent formula for a sub-formula embedded in a larger formula without changing its meaning. So if we identify a sub-formula and we know that there's some other formula that sub-formula is logically equivalent to, then we can put that other formula in there, and the result of the overall formula will be unchanged. And then finally, the rule of transitivity says that if P is logically equivalent to Q, and Q is logically equivalent to R, then P is logically equivalent to R. Okay, then, and again, that's a sort of like a meta law of these logical laws. So these were all taken from the scientist book. I'll be posting these up on the Brightspace, and you'll be making use of these in your transformational proofs, and then later on in your inference proofs. So by the end of the module, you'll be fairly familiar with them, I hope. So let's see how we can use these logical laws. Okay? So here we have not P or Q, or not P and Q is logically equivalent to not P. So on the left-hand side, we've a fairly complex formula, but on the right-hand side, we've a much simpler one. So let's see how we can use the logical laws we've just introduced to prove that this holds. Now, there's a number of ways we're going to present this. The first way is we're going to actually have both the left-hand side and the right-hand side in play, as it were, all the time. And eventually we're going to try and make one side look like the other side. Now, one of the things I forgot to mention in the logical laws is that I presented the logical laws with symbols like P and Q. Those symbols can stand for prime propositions, but they can also stand for sub-expressions, no matter how complex they are. So if P is some sort of logical expression, then as long as we've exactly the same logical expression there, then that we can use that formula, we can apply that formula. Okay, so we start off with the left-hand side. We start off with the leftmost expression on the left-hand side, which is P, not P or Q. I mentioned if we have a negation outside brackets, it's an invitation to apply one of De Morgan's laws. In this particular case, it's De Morgan's second law. De Morgan's second law says that not P or Q is logically equivalent to not P and not Q. So we can apply De Morgan's second law, and we can replace this piece in red here with this piece in blue. So this sub-expression in red gets replaced with this sub-expression in blue, and we get this second line. And whichever technique we use to present these proofs, on the right-hand side, we're always going to have the explanation of how we got to that line. So in our proof presentation, we'll always explain how we get from one line to the next. And each line in a transformational proof is usually going to be the application of a single logical law. Sometimes if it's simple application, we might roll two applications of logical laws into a single line. But in most cases, we'll have one application of a logical law to get from one line to the next. So to get from this first line to the second line, we've applied De Morgan's second law to this expression to get this expression, and now we have this expression on the left-hand side. If we look at that second line, the left-hand side of that second line, we've got an expression and a second expression, or the first expression and a third expression. Now, it doesn't matter that the first expression has a negation in it, and it doesn't matter that the third expression is a negation of the second expression. Okay, or the second expression is a negation of the third expression. That doesn't matter. Okay, as far as we're concerned, we're just applying, it's like a pattern match. We're looking for something and something else, or first something and a third something. And that corresponds to the right-hand side of one of the distributive laws. In particular, P and Q or R is logically equivalent to P and Q or P and R. So a first thing and a second thing, or first thing and a third thing. And that's logically equivalent to the first thing and the second thing or the third thing. So we can replace the thing that's in this form with a thing in this form. So we do substitution. So we have P is not P, Q here is not Q, and R is just Q. So we have not P and not Q or Q. So it means that we can replace this expression on the left-hand side here in red with this expression in blue, and we get third line here. And that's done by the distributive law. In fact, to give it its full title, it's the distribution of conjunction over disjunction. Okay, so then we have the third line. Then we can apply the law of excluded middle. The law of excluded middle says that P or not P is logically equivalent to Q, to true. P or not P is logically equivalent to true. And what we have here is we've got something of the form not Q or Q. Now, strictly speaking, we should swap the two of those around first using the law of commutativity. And in the notes, I think I've done that. But if we apply the law of excluded middle, we've got a formula here combined with the negation of the formula using disjunction, and that's logically equivalent to true. So this sub-expression here in brackets can get replaced by true. So we have not P and true is logically equivalent to not P. Now note that when we apply one of our logical laws to a sub-expression of an overall expression, the rest of the expression isn't touched. So for example, when we apply De Morgan's second law to this sub-expression, not P or Q, we didn't touch this sub-expression, not P and Q. Now for the distributive law, it was the entire left-hand side here which was involved. So so everything was involved. But to get from the third line to the fourth line, we had not Q or Q, and that gets replaced by true, but this not P isn't touched. It remains unchanged. Yeah?
Is using true and false not not obeying the rules, the grammatical rules of propositional logic, though? Because we're only supposed to use identifiers and connectives.
Yeah, so I'll come to that in a minute. Okay, it's a good question. I'll come to it in a minute. Okay, so we've got from line 3 to line 4 by application of the law of excluded middle. Then one of the laws of simplification says that if we have a proposition combined with true using conjunction, then we end up with just a proposition. In other words, P and true is logically equivalent to P. And so we apply this to the entire left-hand side here. We've got an expression and true, and that just gives us the expression. So we get from line 4 to line 5 by application of one of the laws of simplification. And at this point, the left-hand side is equal to the right-hand side, and we're finished. Okay, so what we've done is we've applied a number of our logical laws, De Morgan's second law, the law of distribution of conjunction over disjunction, and we probably should have applied the law of commutativity of disjunction, we've applied the law of excluded middle, and we've applied the law of simplification to show that the left-hand side is actually logically equivalent to the right-hand side. So this has a number of things to point out about this. So first of all, we've applied these logical laws in a systematic way. Okay, and when we apply a law, we're doing a pattern match. we're looking for something that's got the same pattern as either the left-hand side or the right-hand side of one of our logical laws. And if it does do that match, then we can replace either use the right-hand side, use the left-hand side of the formula, or use the right-hand side of the formula and do the variable or the symbol substitution. In the course of this proof, we tend to only apply one logical law in each line, but we always state which logical laws we're going to apply. Sometimes, for simple proofs, we might have, or for simple steps, we might have more than one logical law being applied. And in fact, it's usually the case that we have a logical law being applied more than once. Overall, however, if you look at the very first line, we have got 1, 2, 3, 4, 5 operators involved and 2 prime propositions. So we've got 2 negations, 2 disjunctions, and a conjunction involved in the left-hand side. And that can be, and 2 prime propositions, and we've shown that that's equal to, that's logically equivalent to not P. So that's logically equivalent to a single proposition and a single operator. Yeah?
Are we going to have to memorize all the different laws, or like will we have a copy of them? Or like quizzes and stuff?
So, as I said, you will have there'll be a sheet available on Brightspace, which is just a copy of the page from the scientist book as it happens. And for the tutorial sheets and for the first number of assessment exercises, and that number is either 3 or 4, I can't remember, you will have access to the logical laws. And later on, there'll be inference rules, which you'll be using for inference proofs, and you'll have the access to the sheet for those as well, for the first number of assessment exercises, until you become familiar with them. For the final assessment exercise, you won't have access to them. But that'll be the middle of December, and you'll know them off by heart at that stage anyway. So the big picture, I guess, result from this transformational proof is that we've transformed a fairly complex compound expression into a much simpler. It's still a compound proposition because there's a negation involved, but it's much simpler. We've only 1 prime proposition involved, and we've only got one operation near negation. Now, the question that was asked earlier is this not disobeying the syntax of the propositional logic that we had previously, where the only symbols we had in the propositional logic were symbols that stood for prime propositions or for propositions? And strictly speaking, yes, that's true. So what, in fact, we've done, even though we didn't announce it, is that we've extended our propositional logic language to include 2 special symbols, true and false, to represent the 2 truth values we have in our logic, namely true and false. So we've extended the propositional logic language. It's a bit like saying that we've got a certain language for expressing expressions in algebra, in arithmetic, and then we extend that to include numbers as well. Okay, so in the same, analogously to that, we've extended our propositional logic language to include the symbols true and false to represent the 2 truth values that we have in our logic. Okay, we're going to do another example, but we'll leave that there for now. That's the one we'll do next.